You've probably noticed we're in the middle of a massive AI boom. I mean, every single week it feels like a new model comes out that just completely shatters old records. But this incredible pace, it raises a really big question. Are the tests we're using to measure these AI systems, are they actually telling us the full story? Let's dig in.
So think about it like this. We have AI models right now that can pass the bar exam, no problem. They can get top scores in these crazy advanced math competitions. And they can write code like a developer with decades of experience. On paper, they look like absolute geniuses. But what happens when we take them out of that quiet exam hall and throw them into the messy, unpredictable real world? That, my friends, is where things get really, really interesting.
Okay, so to get why our old tests are kind of falling apart, first we have to appreciate what we're dealing with. This is a completely new breed of AI, and it's being trained in a totally different way.
You know, the early large language models, they were basically trained by just sucking up massive amounts of text and code from the internet, the whole public web. But today's frontier models, they are being raised on a much, much more sophisticated diet.
This is a pretty fascinating peek under the hood. It shows the training data for a recent NVIDIA model, and the big takeaway is what it's being fed. Just look at the emphasis here. Nearly a third of its data is what they call synthetic data for STEM fields. That means problems and solutions generated by other AIs, not just stuff they scraped off a website. Then you add another third for coding, and you can see these models are being deliberately drilled on complex, reasoning-heavy problems.
And here's another really cool technique. With their 5-4 reasoning model, Microsoft didn't just give the model questions and answers. Nope. They used a more powerful teacher model to generate these super detailed step-by-step reasoning demonstrations. They're literally teaching the model how to think, not just what the final answer is. It's a huge difference.
So you've got these incredibly capable new models. They're raised on this diet of complex reasoning, and what's the inevitable result? Well, they've started to completely break the old scoreboards we used to measure them with.
This quote from a European Commission report just nails the issue perfectly. When all the top models are scoring pretty much 100%, the benchmark becomes saturated. It's kind of like having a weight scale that only goes up to 100 pounds. It's useless for telling you the difference between someone who's 150 pounds and someone who's 200 pounds. The test just can't distinguish between good, great, and absolutely amazing anymore.
And all of this has led to a major shift in how we think about testing. We're moving away from the old school model of testing AI like a student taking a multiple choice exam, all by themselves in a quiet room. The future of AI evaluation, it looks a lot more like an interactive gauntlet. It's a dynamic simulation where the AI has to collaborate, it has to adapt to a changing world, and often there's a human in the loop.
So what do these new interactive gauntlets actually look like? Well, as it turns out, researchers are getting seriously creative.
Let's take a look at a new benchmark called Tau Squared Bench. The big idea here is something called a dual control environment. So forget the AI being the only one with access to tools. In this setup, both the AI agent and a simulated human user can act on a shared digital world, and they each have their own set of tools. It's specifically designed to mimic real-world collaboration.
Okay, let's make this real with a tech support example. Say you tell the AI your phone has no service. The AI agent figures out the problem and tells you, hey, try toggling airplane mode. Now, here's the key part. The AI can't do it itself. You, the user, have to use your own tool in the simulation to actually perform the action. The AI then has to check that the environment has changed and then figure out what to do next. It's a test of communication and coordination, not just book smarts.
And wow, the results are pretty stunning. This chart shows the performance hit that top models take when they have to switch from working alone to actually guiding a user. For GPT 4.1, that's an 18 percentage point drop. For another model called O4 Mini, the drop is even bigger, a full 25 points. This basically reveals a massive blind spot. Today's most powerful AIs, they are brilliant soloists, but they really struggle when they have to be good collaborators.
And it's not a one-off thing. Other benchmarks like Terminal Bench are pushing things even further. Just look at these tasks. We're not talking about multiple choice questions. This is about deep, complex, real-world engineering challenges, like building an entire operating system from the source code or cracking a password. These are the new, incredibly difficult final exams for AI.
So this brings us to the final piece of the puzzle, because this isn't just some academic exercise. This race to build better tests has huge real-world consequences, especially when it comes to policy and regulation.
See, regulators, like the ones behind the EU's AI Act, they need a trustworthy way to identify the most powerful AI models, the ones that might pose what they call systemic risks. And their term for this is high-impact capabilities. But how do you actually measure that?
Right? That is the billion-dollar question. You've got scores from math tests, from coding challenges, from these interactive simulations. They're all on different scales. So how do you possibly combine them into one single robust score that tells you, yep, this model has crossed a critical threshold?
Well, one really promising solution is a statistical method called Principal Component Analysis, or PCA. The best way to think about it is like an AI Olympics. An athlete might be amazing at the 100-meter dash, but just okay at the javelin. PCA looks at all their scores across all the different events, and it mathematically finds the single most important underlying factor that explains their performance, their overall athleticism. For AI, that factor is its general capability.
So what PCA spits out at the end is a concrete, data-driven formula. It analyzes results from a ton of different benchmarks and then assigns a weight to each one based on how well it predicts that overall capability. You can see right here, for example, that GPQA, a benchmark full of graduate-level expert questions, it gets the most weight. That tells us it's a really good indicator of a model's general power.
And the final result is this: a clean, ranked list of AI models based on their underlying general capability. This gives policymakers a data-driven way to draw a line in the sand. Models that score above the threshold get designated as having high-impact capabilities, and they might get some extra oversight. Models below it don't. Simple as that.
So what does this all add up to? Well, what we're really witnessing here is a kind of coevolution. It's a race between AI capabilities and our ability to actually measure them. And it's a cycle that just keeps feeding itself. New models get trained on harder problems, and eventually they master our existing tests. So in response, researchers have to invent even harder, more realistic benchmarks to find the new limits. And then what do the AI developers do? They take those new, harder benchmarks and use them as training targets for the next generation of models. The whole cycle just continues, getting faster and faster with every single turn.
Which leaves us with one last really crucial question. This capabilities race is pushing the boundaries of what's possible at a truly mind-boggling speed. But as we build these ever more powerful tools, the ultimate test isn't just about measuring their intelligence. It's about making sure our own wisdom, our foresight, and our ability to govern this technology can keep pace. Now that is the race that truly matters. Thanks for watching.